Okay, so what I'm going to talk about today is MCJIT and debugging JITed code that's produced by LLVM. A little bit of introduction. I'm from the OpenCL team in Intel that develops the Intel OpenCL SDK. It's based on LLVM. This is a multinational team. We're based in Haifa, Israel, but we have people in California and Russia and Canada. This work I'm describing is done in collaboration with a team in Canada. So, just to provide a little bit of context, I want to describe in a few words how our compiler uses LLVM. So, we start at the front end. We use Clang, modified Clang that's able to parse OpenCL to produce LLVM IR, which we then optimize with the standard optimizations of LLVM as well as some specific internal optimizations we are doing. One of them was presented by my colleague in the previous developer meeting, the vectorization, which is a bit different in conceptually from what was presented here earlier, because it's quite specific to OpenCL, not general for any code. After that, we do the pretty much standard code generation, tweaked here and there, and then we JIT the resulting code into memory to execute it. So we have the OpenCL library, which is like built-ins and heavily optimized building blocks that gets injected into this process in two places. One of them is on the LLVM IR level. Some code is just written in a way that is compiled into LLVM IR and can then be optimized together by LLVM together with the user code, OpenCL code. And the other way is we have some built-ins written in C++, and these are dynamically linked into the resulting x86 code. It's kind of like a shared library, simplified in a sense. It is important to present because I will later address some issues of relocations and stuff like that MCJIT has to do, and this is important, that step. Okay, so what was our motivation to even get started with this work? We are working on tools for OpenCL. It's part of our team's job. We produce not only the OpenCL implementation that can run on actual user machines, but we also want to produce tools for developers who develop OpenCL code. And one of the most important tools people want is a debugger. And this is something that is a high priority tool for us and for other companies that provide tools. So in the currently released version of our product, we actually do have a debugger. It's not a real debugger, like in the sense that I will describe later in this presentation. It's based on instrumentation. If anyone is interested, we can talk about it later. But to add a lot of features for users, to give them a debugger they are used to, well, in a sense, GDB, to enable debugging OpenCL code with GDB, we engaged in this project. And it's expected to be available as part of one of the next releases of our product. So what does LLVM currently have for debugging? Not a lot, unfortunately. there is a JIT interface that was added to GDB together with a registration interface in LLVM. It was based on the same work. But the only thing it currently enables, if you just take trunk LLVM and try to JIT code out of it, is to see stack trace in case of a crash. So if you have some C code, you compile and JIT with LLVM, and it does some, say, null pointer dereference and crashes the system, you should be able to open a stack trace or run it under GDB and to be able to see the stack trace where it crashed, like which function crashed, basically. It's helpful, but it's not much. When we started to think about this, we consulted a lot with the LLVM community on the mailing lists. And one of the directions we explored, and others have looked to previously also, is to add debug information generation into the current JIT path. But this turns out to be a lot of work. And not only it is a lot of work, it also duplicates a lot of work that already exists in the static compilation path of LLVM, MC. And as we understood, and later it became even more obvious that in the future, these encoding paths, MC and JIT, have to become one, and well, MC and the other one is going away at some point, we realized that the better approach for this would be to leverage the existing debug information emitting capabilities in LLVM, which already exist in the MC path. Actually, LLVM, when it functions as a static compiler, it produces code that can be debugged with GDB or LLDB and maybe other debuggers also. So this is mostly what this work is about. Okay, so a few words about MCJIT. MCJIT was presented briefly as part of a really nice presentation on MC in the previous developer meeting, in the American one by Apple folks. I will just say in a few words more in depth how it works, so we have a common base of discussion. So basically, the static compilation path, what happens when someone uses LLVM to just compile an object file, it goes through the MC module, which emits code either directly in binary code or assembly, and can do all other cool stuff, but this is the relevant part, its ability to take code-gen data structures and emit actual binaries from them. And then it gets written into an object file or assembly file on disk, and here it ends. There is currently a very welcome effort to have a linker in LLVM, and maybe if we were engaging in this work 2 years in the future, we could have leveraged this linker, but currently we can't. So what does MCJIT do? MCJIT says, okay, so we have an object file in memory before it gets written to disk, so let's not write it to disk, let's execute it. So we'll take this in-memory entity, which is encoded in a standard object file format, for example, ELF on Linux or Mac, however you pronounce it, on OS X. And we perform dynamic linking and loading of it to be able to actually run it. So what was the motivation for MCJIT? The first two bullets here are taken from the Apple presentation from the previous developer meeting. So one is to avoid the duplicate encoding paths that currently exist in LLVM, one for JIT and one for MC. The encoding, I mean the part that takes cogent instructions and actually says how they're laid out in memory, how instructions are encoded and other sync modes and all that. A lot of this is currently duplicated. This is also a very important bullet for us because when we want to enable future instruction sets for Intel like AVX2, there is work that's being done in the MC path, but the JIT path doesn't really get much love any longer, right? So we just have to take it and port it to JIT to be able to let our product keep working, and we don't want to do that anymore. And the third bullet here, we added it. This is debugging. So we will take MCJIT and use it as a tool to enable us to provide debuggable JITted code. Okay, so a few words on how MCJIT works. Now, a short disclaimer. This slide and a few after it have some code like method names and class names. I don't intend to spell this out or for anyone to exactly understand now what each other does. It's here for reference because you probably know better than me that LLVM is a huge code base, not a lot of documentation about it, and sometimes it's really hard to find parts that you want to work on. Like, I want the debugging part, so now you have to think up strings that you have to grep in the code until you find some files that appear familiar, and you go from there. So the point of this is for these slides to serve as a reference later for interested people, and these are all good starting points to understand which parts of the code are concerned here. So MCJIT is just another execution engine. Execution engine is an interface in the back end of LLVM, like the absolutely last part. You have the interpreter there, and you have the JIT there, and you also have MCJIT. It can be customized with target information and a memory manager. I will mention why memory manager is needed later. What it basically does, it runs the same passes the static MC path runs, but eventually it creates an object file in memory. So I will focus here on ELF, which is what we do, but it applies the same for other object formats as well. And at the last step, it uses a module that's called runtime dynamic loader that performs the dynamic linking and loading of the code and enables it to run. So what is the problem here? I mentioned it briefly before, but it's important to understand. MC emits an object file. This is the .o thing you have when you compile GCC -c, say, okay? It can't run, right? It has to be linked, and then it has to be loaded. These two steps can be done in one, but generally, in our normal compilation flow, we take several object files, .o, and we link them together, say, into an executable or, more interestingly, shared library. The linker resolves all kind of references from one object file to another by means of relocations and all kinds of magic. After that, when we have an executable or shared library, it can be directly executed. There is a dynamic loader that gets executed by the operating system in user space, actually, and it loads this executable. It finds the shared objects you need. It looks at all the LD preload, LD library path flags you can customize this process with. It does some relocations also, whether for position-independent code or not. And then it passes control actually to the application to run. So here there is a short listing of the kinds of stuff the loading has to do, allocate sections. Some sections, for example, BSS or common symbols are not actually present in the object file. The ELF header just says, okay, I have a section here. It's not allocated, and so the loader has to allocate it, and maybe probably initialize it with zeros, right? Otherwise, object files would be needlessly huge for empty data structures. So what is the solution MCJIT provides for this? The solution is this runtime dynamic loader I mentioned. It's a linking loader. There is such a thing actually on many historical, but I think there are even some machines now that have a linking loader in one step, although usually it's done in two. What it does is I call it just enough linking to make the object file run. So there's absolutely no handling of all the general purpose stuff LDSO does or the linker does. Only those features that are needed for this generated object file to run, okay, as the sole executable. It's not unlike what JIT does. JIT also does it, but in a very different sequence. So here again, some code to let interested people find stuff in the code. There is a generic interface, a runtime dynamic loader implementation that can be implemented for different object files. So what's currently inside is implementation for Mach and for ELF. Oh, sorry. Okay, so a couple of words what's needed to dynamically load at runtime ELF objects. I mentioned allocation of sections previously. This is a very important step. Some sections can't be, the object file can't just be copied to some other place from which it can be executed, because these sections are not really in memory, right? So if you allocate an empty array of 5 million elements in your code, the object file won't actually get those, I don't know, 20 megabytes of empty data. It will be tiny because the ELF has provision for that, and the linking loader has to do that. Recording of actual absolute addresses of symbols has to be done because it is known when the object file is loaded. It is not known when MC compiles it. So it depends on architecture, right? You have RIP relative addressing on x64, or we don't have it, or on x86. ARM and other architectures have tricks of their own. But the point is that eventually the code has to know what the absolute addresses of symbols are, and this is done via relocations that the linking loader performs. Okay, so that was the loading. Now I'll stop here to say a few words about what was there before, what is there now, and what is planned. So when we started working on this, Apple had a partial implementation of MCJIT for their platform, for Mach objects. It didn't pass all the execution engine tests yet. I think they use it for LLDB at this point. So what we added an implementation for ELF, focusing on Linux currently. And we also refactored a lot of the code to make it more common with the Apple implementation for Mach. I will mention a few more words about the status later. So debugging. As I mentioned, GDB, since version 7, already has built-in support for debugging JITed code. In a few words, it works like this. It works similarly to the way GDB knows how to load shared objects. So you're probably all familiar with when you start GDB on some executable, and then you ask it to put a breakpoint in a shared object that was not loaded yet. So it will ask you if you want to make it pending on shared object load, right? So it's the same with JIT. What GDB does about shared objects, it puts a breakpoint inside the dynamic loader. It knows where to put it. It has some known routine there that it knows its address. And it uses a data structure, this LDSO fields with the object files it loaded and the dwarf debug info for them. So the JIT interface does the same. What was added to GDB is a known symbol that GDB puts a breakpoint on, and if the loading code actually implements it, then when new objects get JITed, GDB can find out about it and read the debug information for these JITed objects, and the result is that JITed code is treated pretty much the same as shared libraries. You can put, I will show a short demo later, you can put a breakpoint in your C code that you compiled with LLVM and JITed. It will ask you pending, yes, and then you can actually break there. So again, I will not repeat how this works. You can take a look. All right, so demo. I realize maybe not everyone sees it in the back, and I'm sorry. I chose the most failure-resilient method of demos, screenshots, okay? If you want the slides immediately, I can send them to you. Just come ask me after the talk. So this is a simple iterative factorial computation and a simple main function in which, in order not to get dirty with libc, I accept parameter from argv and return it in the result in the return code of the program. So what do I do with it? I take Clang and I compile it with the -g flag as usual into LLVM, because I'm going to debug it with debug LLI that executes the LLVM resulting from this. What happens at this stage is that Clang generates debug metadata into the IR. There is a very good and documented format for debug metadata that describes debugging information at the IR level. And then LLVM takes this metadata and translates it eventually to dwarf that gets placed into the ELF image that MC generates in memory. So I'm running LLI with MCJIT under GDB, passing it 5, like computing factorial of 5. I can put a breakpoint on a line in this code, and again, it says make breakpoint pending on future shade library load. Yes. When I run it, it actually stops there, and I can do anything I do in GDB. I can look at variables, look at the backtrace, and see the JITed function name with line, with parameter values. I can step a little, put a breakpoint in a different place, and exit. So there's a quiz here why it returned 170. Okay. Remaining challenges. Efficiency. There's quite a bit of copying going on currently in MCJIT that can be reduced. This is mainly because some code has to be allocated as executable but not readable, not writable, sorry, and some code has to be just readable, not code, I'm sorry, data, and some data has to be writable and readable. It's not easy because MC gives you an ELF just in a buffer, right, like an array. It's read-write. So we have to use, LLVM actually exposes some OS facilities for allocating RWX chunks of memory or non-executable chunks of memory, stuff like that. This can be improved. Another thing is that MC compiles the whole module. Because MC is used for the static compilation path, it can't know in advance which code is going to be used, right? This is as opposed to JIT, that you ask JIT for a function, and then it goes on either lazily or not. It compiles only this function and the other functions reachable from it. Okay, this can be handled on a few levels, maybe even on a LLVM level. Currently, there is no handling for this in the code. We actually JIT the whole thing. We, in our OpenCL implementation, rely on the fact that we actually analyze the code earlier on the IR stage, and then the only thing that reaches this code emitting step is what we need, and not all the code. There is a problem of Windows. I was pestering the mailing list about it a couple of months ago. Our current plan is to generate ELF on Windows as well. It works for us in our branches, and we plan to go forward with it in our product. I would like to submit this back to LLVM as well, because honestly, I don't want to handle COF, and I also don't see a reason to do that. ELF works great on Windows. This is JIT after all, right? So JIT, it just generates a blob of executable code without any structure or official formatting. So there is no real reason why ELF can't be JITted on Windows. What makes it hard is that the LLVM triple enforces COF generation on Windows. It detects the platform and generates COF. So in our branch, we just patched it to generate ELF, but probably I suggested to add another field to the triple where there is already a flag for Mach, to add one for ELF, but it wasn't accepted. Some very good reasons were raised. I guess it will take a more deep work to approach this in the long run. And there's also the issue of multiple modules, that currently MCJIT only knows how to load one module, because loading multiple modules means that MCJIT has to do actual linking. And we don't want to go there currently. We'll just wait for LLD to be ready, and then it can be enabled. But we don't really suffer too much from it, again, because in OpenCL we currently don't have this problem. All right, so I initially planned to fill this slide, but it proved to be impossible because it's in constant flow. Just tonight, another step of this was approved, passed review, and I will commit it when I get back. So the status right now is the following. What we have working in our internal repository is MCJIT on ELF on Linux that passes all execution engine tests, similarly to all JIT, works fine, and allows debugging with GDB. The demo I showed is taken from the branch. I just ran our version of LLVM and it debugs. In LLVM, in trunk, currently there is a partial implementation. There is another developer from another company that started working on this, and we are collaborating with him as well. He committed some patches, and we commit some patches, so it kind of goes in turns. His work depends on what we did, and now we have another chunk of work that depends on what he does. It's a nice example of collaboration. And this brings me here that we would really appreciate help with reviewing these patches. From what I've seen in the mailing list and the emails I received, MCJIT is a topic a lot of people want for various reasons, but in practice it's pretty hard to get anyone to review it. I suppose because it's an area of the code that not many people are familiar with, and that's all right. So we currently rely on reviews from the Apple code owners in this area. And even the fact that we have another independent developer who is not in Intel working on this, and he's reviewing our patches and we are reviewing his, it helps a lot. We have enough manpower to move this forward really fast. The real thing lacking is reviews, right? So if you want to work in this area, it's more than welcome. Reviews are the first priority. This is it. Questions?